Hi, I'm Lisa Lippincott, and I'm here to talk about perspectives on contracts. Now, for those of you who have seen me speak before, this isn't my usual sort of talk about the about achieving program correctness. This one came about in an unusual way. This summer in St. Louis at the WG21 meeting, I gave a presentation to the language evolution group about the contracts proposal, about why it has been so hard to achieve consensus with the contracts proposal, and why some parts of it just seem weird to people even now. And that was well received there. I was asked to bring it here, and so here I am. If you want the other kind of talk, I gave that earlier this year at cplusplus Now. It'll be out on video soon. You can go look for it. So here we go. Some time ago, I was taught an algorithm for the subtraction of decimal integers. Maybe you were too. It was part of the new math, they called it. And towards the end of teaching this to me, my teacher made what to me seemed a very strange suggestion, that after performing this algorithm, I should add up two of the numbers and see if the sum matched the third, as a way to detect any error in my execution of the algorithm. I was not a fan of this idea. This seemed to me like doing more work while making no more progress. It seemed like a waste of my valuable time and effort. If I had known the word at the time, I might have said it was redundant. And this quite possibly was my first introduction to the idea of assertion. And I had learned the first thing to know about assertions, which is they are redundant. If you're writing something that's not redundant, don't use an assertion. I had experienced, but not comprehended, I think, one of the other things about assertions. People are going to disagree about assertions when they have different points of view. I had the point of view on the left side of the slide represented by the mechanic. I valued efficiency. I wanted to minimize the impact on my time and energy. My teacher valued something else. My teacher valued error detection. And error detection requires redundancy. This is a basic fact of information theory. There is no error detection without redundancy. So I wanted to get rid of redundancy for efficiency. My teacher was suggesting that I add redundancy in order to have error detection. These two points of view cannot be reconciled. They are fundamentally at odds with each other. They can only be chosen between. And so in C, we have the assert macro, which lets us choose between these things later. After our source code is written, we can decide whether it's to be compiled ndebug or not ndebug. And the mechanic, when you're in a mechanic mood, you will define ndebug. The assertions will be ignored in our modern parlance. And you will have very efficient code. When you put your detective hat on, when you are trying to detect your bugs, you let ndebug be undefined. The insertions are enforced in our modern terminology. and you give up that efficiency in favor of error detection. And the C standard basically says two different things about how the assertion behaves, and it has to do with whether debug is defined or not defined. And in C, that wasn't too bad, at least back then. I haven't paid that much attention to how C has evolved, but because you could turn this on and off on a translation unit by translation unit level. You could say, yeah, I want to debug the things in one file and just turn it on there, turn it off elsewhere. It's a nice lightweight choice. You don't have to make one decision for everything. We would like to have that in C++, but we broke it. In C++, we get one decision for your entire program. And that makes it really kind of a chore to flip that switch. Your program goes from being very efficient to very inefficient, even if you're just trying to focus your debugging on a piece of a big program. So how did that happen? Well, it happened because in C++, so there are these 2 points of view for the assertions, where in one point of view, the compiler says, oh, nothing's going to happen there. The other point of view, the compiler sees that the execution might be halted under some circumstances. And in C++, we created contexts where two different compilers, two compilers running with different settings can end up seeing the same assertion. We put them in, if you put them in an inline function or in an instantiated template, those things are in the header files. More than one compiler is going to see them. And this becomes a problem, particularly when the compiler that produces the code is following the left version, and the compiler that is calling the code is following the right version, but thinking that the other compiler also followed the right version. And you have crazy optimizations ensue. Your program can very easily go wrong. Whose fault is this? Officially, it's yours. You have broken the one definition rule by doing this. And you didn't mean to, but nobody's going to tell you that because we are very bad at diagnosing violations of the one definition rule. So our first task was to get rid of this problem, to make it so that one compiler doesn't know what the other compiler is doing, can't make assumptions about what the other compiler is doing. And so we came up with a way to word this in the standard that keeps one compiler from optimizing based on something the other compiler didn't do. We found a unified expression in the standard. These aren't the exact words, but a unified expression in the standard that says that both compilers can agree upon. But to make both compilers agree, it has to be rather vague. And if you read this, that is a really vague thing to say about what the assertion does. But it covers both ignoring and enforcing. And that's approximately what we say about what the assertion does in the newfangled contract assert does in the standard. And that's what lets us get back to choosing one file at a time, one translation unit at a time, whether we have our detective hat on. The compilers agree on something, but they agree on something that's very vague. And this, in a nutshell, is the source of all the contention, I think, or almost all the contention over assertions. The thing that we standardize needs to be a big circle encompassing many points of view. But individual programmers have particular points of view about how they want their assertions to behave. Now, those points of view move around depending on their circumstances. You're debugging, you want them to behave one way. You're in release, you want to have them to behave in another way. And there are a bunch of different circumstances that you might be shifting between. But it's very tempting when people read the standard to be set in one or two of these points of view and not appreciate how wide the circle should really be. And this is really the sort of contention we have in the community. So from the standards point of view, there's one program with a range of conforming behaviors. The standard is the big circle. To programmers, there's a bunch of different points in there, and they seem very different to programmers. Programmers care about that. And that's why the circle seems so big. I mean, we're not affording a numerically large affordance for implementation-defined behavior. There is nothing numerically bigger than the implementation-defined behavior that was already there. But this one feels big because you care. It's because shifting around in this circle, you feel like that makes kind of a big difference to me. So in a nutshell, our contracts facility has to allow a single program to have significantly different behaviors. And even here, there's 2 points of view represented in this single sentence. That is, from some point of view, it's a single program. The contracts, the assertions you put in, don't make a difference to the program. It's the same program after you added assertions to it. But from a different point of view, whether those assertions are enforced or not matters. And so when you're debugging, you care that your assertions get enforced. And when you're optimizing for efficiency, you care that your assertions get ignored. So there's this other point of view from which you're constantly making changes to the program without without editing the source code. Now, we need a way to navigate between these points of view. When you're writing an assertion, how do you deal with the fact that there are these 2 points of view? And really, there are 2 principles. To make sure it's the same program, whether the assertion is there or not, whether it's ignored or enforced, your successful assertions should do nothing significant, even if they're enforced. Now, that can't mean that they do nothing when they're enforced. It's not possible to evaluate an expression without doing something. A little entropy is released into the universe, heat increases, and small things change inside the computer. You disturb the state of the memory manager. Maybe you call sbreak. That's user visible behavior to call sbreak because it's a system call. So maybe these things actually happen. But these are all little things. Maybe something got moved into a cache that wasn't in a cache before. These are all little things that you're not caring about when you write this assertion. They're not significant things. So there is this dividing line. There are going to be some effects, but they shouldn't be effects that are significant to you as a programmer. On the other hand, the assertion should say something significant. It should say something that is true and that you care about being true. The difference between the assertion saying something true and the assertion saying something false has to be, at least in some circumstances, something you're willing to halt the program over. So don't say something that is utterly insignificant. So follow these 2 rules, your assertions will be good. And if I was just talking about contract assert, that's pretty much the whole talk. But we had another thing in our remit, which is to add pre- and post-condition support. So for those of you who don't know, these are conditions that sit in between functions. That is, the preconditions are executed, are evaluated, are potentially checked on the way from a calling function to a called function. And postconditions are checked when the called function returns. And the pre- and postconditions form what some people refer to as a contract between the two functions. They express the points of agreement between caller and callee. And this is a powerful technique because if you express the points of agreement between the caller and callee, you know which side the bug is on when you find a bug. You have a clear idea of which function's expectations were not met and whether it had any right to expect that to be met. So this is the basic picture for preconditions and postconditions. That's pretty much what I had in my mind going into the development of contracts. And it turns out to be a problem because in C++, we care about translation units. And these pre- and postconditions are on the edges of functions. They often happen in the gap between translation units, spanning the transition. But that can't be right because they are code. And code is emitted by a particular compiler compiling a particular translation unit. So this is the wrong picture. This can't happen in C++. This is the right picture. There are preconditions as viewed by the caller, and there are preconditions as viewed by the callee. And they are often being seen by different compilers or the same compiler running in a different mode. They will see things differently. The same thing goes for postconditions. There are postconditions as seen by the callee, and there are postconditions as seen by the caller. And this brings us to another point of view on assertions, particular pre- and postconditions. There's a difference in viewpoint that distinguishes backward-facing conditions from forward-facing conditions. Here, backward-facing is the caller-facing preconditions and the callee-facing postconditions, where you are on the side the arrow is coming from. And forward-facing is callee-facing preconditions and caller-facing postconditions, where the arrow is pointing towards your side, incoming and outgoing. So, we are going to distinguish two different viewpoints that see these kinds of conditions differently. One of them is familiar. One of them, you have your detective hat on. You're looking for bugs in your code. And when you're looking for bugs, you want to track them back to their root causes. You are always looking backward when you have your detective hat on. The bug is back there, you want to trace it backwards. But there is another point of view, a safety-oriented point of view where you put your hard hat on. And you put your hard hat on because your head is sensitive to falling bricks. Not in order to keep bricks from falling on you or to make the people above you more careful about dropping bricks. You put it on because you want to divert any bricks that do fall before they crush your skull. That's what a hard hat is for. A hard hat is a forward-looking safety idea. It's looking at the future. It's looking at where that brick is headed and deciding, no, I don't want to let the brick head there. So when your code is sensitive, when you really don't want somebody else's bug to cause a problem in your code, you put on your hard hat and you block things that don't meet your requirements, things that don't meet your expectations, situations that you would like to rely on and it turns out you can't, from getting into your code. So that lets us have two checkboxes. If we have two checkboxes, we have a much more interesting way of pilots. We can have some things, the things that are being tested, the things that you're actively debugging, the things that you think, that's new and it's probably not quite right yet. Put your detective hat on for those. But maybe you have some parts of your code that are like, yeah, it's really dangerous if the bug hits that. So let's stop the bug before it gets there. So two sets of checkboxes lets you compile in some interesting ways. First, if you turn all your checkboxes off, all the assertions are ignored. You please the mechanic. Your code runs very efficiently. If you turn the detective assertions on, you're checking all of your pre and post conditions if you turn on detective assertions everywhere. You're checking the preconditions in the translation unit of your caller. You're checking your post conditions in the translation unit of the callee. Everything gets checked, and you're happy because you detect your bugs. On the other hand, if you turn on the hard hat, you get the same things checked. Everything still gets checked, but they're checked in different translation units now. The callee checks the conditions they rely on, which are the preconditions, and the caller checks the conditions it relies upon, which are the postconditions. And so each translation unit can be responsible can do the checks for the things it cares about and skip the ones that it doesn't care about. And we are going to see situations where you end up mixing and matching, where you're moving from something in detective mode into something that is in hard hat mode. And what do we do there? Well, some people think there's going to be some sort of clever thing that makes sure that things only get checked once here. I don't buy it. That requires trust. This is a situation where we have no trust. We're going from suspect code into sensitive code. We shouldn't be trusting each other. So what I really expect and what we allow in the contracts proposal is that the assertion gets tested twice. We check twice. We can check once in the calling translation unit and check again in the called translation unit. And yes, it's a little inefficient, but efficiency is at the bottom of our list here. It is less important than detecting our bugs, and it's less important than safety, and we have made that decision. So, okay, we can be a little inefficient. And I want to say I'm used to this already because every once in a while I make a kernel call from my code. And I want to put some assertions in, I want to do some checks in my code that I'm passing the right parameters to the kernel call because I want to get it right. And if I don't get it right, I want that sweet, sweet debugging data that comes from putting the checks in myself on my side. But when I do that, yes, I check, but I know the kernel is compiled in safety mode. That's kind of the point of a kernel, is that it's going to check my parameters again before doing anything with them because the kernel has this safety wall built around it. So I'm used to seeing that double check. Well, mostly I only see my side because when I get it right, their side doesn't do anything terrible to my program. But I'm used to the inefficiency of double checking in these situations where my code is suspect to me, and the people who compiled the kernel, they deemed their code sensitive. So how do you make sure that your assertion is just fine even if it's double checked? And I want to emphasize, this is not something that other language features do. You write an if statement. We don't give the compiler the freedom to evaluate your if statement twice before branching. That would be wrong. But assertions do. They're a little different. They're not if statements. So how do you deal with that? How do you deal with that uncertainty? Your assertion should do nothing significant and say something significant. Follow these rules, you'll be fine even if your assertion was repeated, because repeating it will do nothing significant. Now, this same diagram that I've been showing you also comes up in the case of virtual calls. Took us a long time to get this into the proposal, but it's in finally. And the reason it took us a long time really was getting people used to this picture, where in a virtual call, or any sort of indirect call, but we haven't done function pointers yet, in any sort of indirect call, the caller has a different set of preconditions and postconditions than the callee does. The caller in a virtual call sees the base classes pre and postcondition. It's following one contract. But the called function, the overrider, may be following a different contract. And really, the base class contract can be very specific about what the caller is doing, but it's more general about what the overrider is doing, because it could be a whole bunch of different overriders fitting into this same sort of call. Now, the contract on the overrider side can be very specific about the overrider, but it knows less about the base class. I mean, it knows it's coming from one of these base classes. That there could be a lot of base classes, it could be multiple inheritance. So you know less about it less about the caller when you're on the overrider's side. Now, for safety, this works just fine, because everything that you rely on has a place where it can be checked just before you rely on it. Your hard hat mode works fine this way. But there is an issue that comes up when you put your detective hat on, because there are three kinds of bugs the detective wants to distinguish. One is a problem in the caller and the base class preconditions. If they fail, they indicate a problem in the caller. Another is a problem in the callee. Well, the callee's postconditions are definitely are there to find problems in the callee. But we have another kind of problem that can come up in these indirect calls, and that is a problem of substitutability. If the contracts don't match up, it's possible, the contracts are not the same, it is possible to fall in the gap where you satisfy the base class preconditions, but not the overrider's preconditions. Or you satisfy the overrider's postconditions, but not the base class postconditions. And this really is a problem in how you design your inheritance. It is a gap in Liskov substitutability. And while there is some argument in the committee about whether Liskov substitutability is something that we want to enforce in some general theoretic way or in a specific, you actually hit it at runtime way, this finds the spot where you actually hit it in runtime. So if you actually fall into that gap, you know your program is wrong. It's not just there was some other assumption in your head not expressed by any precondition or postcondition that should have saved you. So we would like in detective mode to be able to distinguish these, to check all four. That's not easy. But you might think, well, the overrider actually has access to the base class pre and post conditions because it knows what its base classes are. And so you could do some sort of check on the overrider's side. That would be great, but something like 40 years ago, we optimized vtable layouts in a way that keeps you from knowing which base class the call came from. So we can't actually get away with this without changing vtable layouts, and I don't really expect that vtable layouts are going to be changed anytime soon just to make these checks happen. On the other hand, there is one situation where we can do the other sort of check, where we can do both checks on the caller side. Can't do it all the time, but there are situations where we make a devirtualized call, where we call a virtual function, but the compiler has enough information to see through that and know which derived class is fielding the call. And if we're in a situation like that, there's this optimization that happens that turns it into a direct call. That optimization does not remove the base class pre and post conditions. I mean, your compiler will ignore them or not as it sees fit, depending on your settings, but those base class conditions are at least there to be ignored. And I would like to see compilers, I say I would like, we don't actually tell compilers what options to offer to users. That's just how things work between the standard and compilers. But I would like to see compilers enforcing all four on the compiler side when they can devirtualize the call. So fingers crossed that might happen. And here we run into a situation like we might be executing those assertions 3 times now just to do these extra checks. How do we deal with it? The assertion does nothing but says something. Does nothing significant, says something significant. So these two principles really at the heart of using assertions well. It'd be nice if we could debug them, if we could find out when we don't adhere to these principles. And we did include a few things in the contract specification to help with this in specialized circumstances where we could figure out a good way to go about it. So let's start with the bottom. How do you know that your assertion is saying something significant? Well, if you're developing new code and new assertions at the same time, you debug them together. Every time an assertion fails, you look at it and you say, well, was that something that was supposed to be true, really? Or was it a bug that happened earlier in my code? And you adjust your assertions. That's okay. But if you're putting new assertions in old code, you get to have a special point of view. You get to have the monocle guy's point of view, where his assertions are his least trustworthy code. If an assertion fails, it's probably the fault of the assertion, not the fault of the old reliable code. Maybe that's wrong, but most of the time, it'll be that because your code is so reliable. And so we include a way for monocle guy to say, yes, I'm going to observe the unenforced assertions in my code. I'll check them, but I won't let them halt the program. And this lets us put new assertions in old code with low risk, because we don't have to run the risk of halting a program. We can just say, yeah, we'll spend a little CPU time figuring out whether or not this is really something we want to assert. And if you see a bunch of these getting asserted, you go in and you look at it and you think, oh, I better fix that assertion most of the time. Once in a while, it's like, oh, that's an old bug that we should have fixed a long time ago. So that brings us up to 3 checkboxes for each file. I think, if my compiler gives me 3 checkboxes like this for each file, I'm pretty happy. This is a question I got asked at this very conference, like, yeah, how much support do I expect compilers to really give me for assertions? And it's like, this is a happy level for me if they give me these 3 checkboxes per translation unit. But haven't really talked about debugging the other one here. How do we know that an assertion does nothing significant? This one's hard. This one is actually pretty hard to test because significance is in the programmer's head. It's not well expressed in our programs at this time. But if we knew something that was significant, we would have a way to do this. We would calculate something significant, and then we would check our suspect assertions, and we would recalculate the significant thing. And if the significant thing changed, that would mean that our assertion did something significant. And the problem with this algorithm, problem with this experiment, is that you have to know something significant. But we do know one significant thing now that we have assertions. The truth of an assertion is supposed to be significant. So if we check some assertions and they succeed, I mean, if they fail, you might as well just say, oh, your assertions are wrong. But if we check some assertions and they succeed, and then check our suspect assertions, and then go back and check the first assertions again, that's doing the experiment. If they fail the second time, it's because our suspect assertions did something significant. Or possibly because they asserted something that wasn't stable. You should only assert things that are stable, because unstable things can't possibly be significant. You can't rely on them later. But either way, this is the experiment that finds insignificant things, or finds assertions that did significant things because they disturbed other assertions that were around them. So we put some leeway into our design. Compilers are allowed, not required, but allowed to repeat assertions that have happened before, as long as nothing but an assertion has happened in between. So compilers are allowed to perform this experiment for you. How would you get this experiment performed? Well, probably something like this. This isn't mainstream sort of stuff. This is a special situation. You can use a fancy compiler option maybe for doing this. Put the ONI in charge of debugging your code, because the ONI can look at things in a cross-eyed way and see your assertion both as saying something significant and to be your control, and as doing nothing significant in order to be the body of the experiment. So the ONI can check these things. And you will notice that in my big circle, the ONI is out on the fringe. We include a bunch of fringe cases. Most of the time, you'll be using things in the center. There's a bunch of central cases that you'll be switching between, but every once in a while, you want to do some fancy debugging thing, or you're in a weird circumstances. You want these oddball cases on the edge. And honestly, maybe nobody wants to be the clown. Maybe nobody ever wants to compile in clown mode. But we didn't put a little dent in the circle just to avoid the clown mode. We don't really expect compilers to offer you the clown mode, and if they do offer you a clown mode, don't use it. Unless you feel like being the clown. So that's really what I have to say. This circle is what causes the problems with getting consensus on contracts. People are all over this circle, and it's very hard to get people to accept that the contracts facility encompasses all of it. Contracts is really our most cubist language feature. You can't understand contracts. If you have trouble understanding contracts, it may be for the same reason you have trouble understanding cubism. You have to accept that it sees things from many perspectives at once. So, thank you for listening. Are there any questions? But please use it.
How would you characterize a mode where you want a contract checked perhaps on a sampling basis? For example, the code is executed in a tight loop. You have a few cycles to spare, but you don't want to check the contract every single time you call this function, and maybe have a random counter or every 1,000th call. Is that? I mean, maybe it's one of the other faces in your.
Yeah. So that one is definitely allowed by our proposal. And in fact, anticipated. I think it's maybe one of the cases that's listed. I mean, Timur mentioned it in his talk yesterday. But do I think it'll be a simple checkbox? Do I think it'll be that easy to turn on? Probably not. That might be a pragma. That might be you write out some fancy compiler option. If your compiler gives it to you, which is allowed, it's probably going to be in a slightly obscure way, not the totally mainstream way.
Hello, I'm interested. What's your perspective on using contracts on a stud function? I know it's beyond the scope of this talk, but it's kind of type erasure.
On a what function?
Stud function, because stud function does type erasure.
The standard library functions. So there is a sense in which we encourage implementers to try that. It is legal for them right now. We're not even changing the standard library spec, but as it is, they can test their pre and post conditions. They can put pre and post conditions on standard library functions, and that is conforming. Some implementers seem to be of the opinion that they might be able to do cleverer things if we don't require them to express their pre and post conditions in that particular way. And so we allow them to do whatever they want with their pre and post conditions, including express them as contracts, but we don't require them. And perhaps with more implementation experience, we will decide sometime in the future that really they ought to. I'm not counting on it. That one, they have some decent arguments.
So there'll be no caller side-facing preconditions.
So implementers can put caller side-facing preconditions in there. They can act as if the contract was there, even if it is not, because violating the contract would be undefined behavior. And undefined behavior lets the implementer do whatever they feel like, including trigger the contract violation handler.
All right, so effectively, that would mean that we have like 2 pointers. One pointer to the function itself, and the other is a pointer to the code that does the required.
So if you are actually using function pointers, you're in a more complicated situation. And no, I don't think any of our likely proposals, certainly not mine, would involve the same function having 2 addresses. Except, the way we often think about these things is that the caller side ones are actually inlined into the calling function. They aren't necessarily inlined into the calling function, of course. The implementation could provide a stub that it calls through, and that could be entirely a local symbol. And in fact, that is an implementation strategy for inline functions and template instantiations that might be interesting. Again, some people think there's going to be clever link time things going on with those. I am not convinced, but you might have a compile flag. I could definitely see having a compile flag that says, when I put this in detective mode and it calls an inline function, if the call is direct, if I'm not taking the address of the inline function, just calling it, emit a local copy of that is purely that has purely local linkage. And call that. And that's perfectly legal to do with an inline function according to rules today. It's only if you actually take the address, everybody has to get the same address of the inline function. So you might end up with, you might have a situation where you can say, yes, it is worth having the code bloat that would imply in order to be absolutely sure I get the contract behavior that I want in my translation unit.
This may be a simple question, but do you see these sort of contracts kind of eliminating the need for assertions just in general outside of these contracts?
So yes, particularly the contracts facility has three real parts: pre and post, which are the preconditions and postconditions, and contract assert, which is really the better version of the assert macro. It doesn't work exactly the same, so you might want to be aware that, yeah, the assert macro is kind of overspecified, and so we're not being exactly like the assert macro, but it really is intended for the same usage.
Right. Thank you.
And sorry about the spelling being so long, but we needed a keyword and we can't make short keywords.
So to summarize, the proposal is a little spotty because I will not have contract executed if I call by virtual function and the compiler does not know what is the actual base, what's the actual function I'm calling, because it's just passed by pointer. And also, I would not get those preconditions. I'm talking only about the backward-facing contracts. Would also not know if they will not be executed if I call the function that is not inline, right? But this is not obvious from the caller point of view, especially the second one.
There is always a compiler that knows the caller-facing conditions. That is, it's the compiler that compiled the caller. There's always a compiler that knows the callee-facing conditions. It's the compiler that compiled the callee. So there is always some translation unit in which those checks can be laid down, with the exception of one unfortunate ABI. And yeah, that ABI is going to have to ignore certain conditions in certain circumstances, but that's sad. They want to fix it, but it's hard to fix an ABI. Anyway, yes, your conditions are always there to be checked, and your compiler will has to give you documentation on under what circumstances your conditions will be checked. But there is probably going to be some variation between one compiler and another. And I think, except for that one unfortunate case that all compilers, I really hope, will give us those 3 central checkboxes.
In terms of syntax, are contracts going to make function signatures really large?
In terms of syntax, you used the wrong word there, I think. Does it make the function signature large? It doesn't. Contracts don't change the function signature. They do, however, make function declarations large, which might be what you meant. Yeah, there is more stuff to put in the header file because we want that stuff up in the header file in order to make the different translation units have a point of agreement. It's much better if there's one place where those things are listed.
Hi, I have a couple of questions. The first actually is a follow-up to the previous question I was just asked. Is there a way to have a declared contract and then reuse it for multiple different files and or functions and things like that? So you have to write out the same logic 100 times?
So the question is there a way to declare a contract and reuse it? And whole contracts, no. This is, to some extent, a beef I have with where we ended up here. It would have been nice if our proposal actually had a concept of a whole contract, and it doesn't. It has individual pre- and post-conditions. But that said, you can write a function that returns a Boolean, and your entire contract can be pre this function called with my parameters, and post this other function called with my parameters, and 2 functions will cover it will cover the situation. So you can get that close now. There is an extension to I have a paper out on how we should handle function pointers. That is not going to happen before 29. That's on the slow road already. We've decided that's on the slow road. But there is an extension to that paper, which might happen in 29 too, I suppose, that would have something that is basically an object that encapsulates a contract. Actually, it's a little bit like a coroutine. People get upset when I call it a co-contract. But it is, that strikes fear into a lot of hearts. But there may be something better where we can get that down to just, use this one thing.
Great. And my second question is, which ABI was having issues with contracts and why?
I don't like to call out particular vendors from the stage.
Do you expect there will be a way to enable contracts in groups, or maybe individually, or only all of them together?
So right now, I expect to be able to enable and disable them on a translation unit basis. I think that's going to be the easiest thing to implement. The people from Bloomberg have some very definite ideas about some sort of tagging or named contract groups. And I don't know if those will make it in or not, but there's definitely a push in that direction. Not in 23. Or 26, sorry.
I noticed in the proposal that the termination in a contract violation does not actually specify calling standard terminate. Was it in implementation defined termination? Is that an intentional choice?
Oh man, we went back and forth on that a lot. At first, it was an intentional choice, and I forget what the reasons were, but those reasons went away. And then we made it a specific choice. And then the implementers said, it's like, no way, that's got to be, we need the flexibility there. So implementers really wanted that flexibility. From a design point of view, the exact mode of termination wasn't important to us, and you shouldn't be relying on it. So that's the way we went. I will say, don't do this, because you shouldn't rely on an exact mode of termination. If you really wanted an exact mode of termination, install a violation handler and terminate the program yourself. And then you will get exactly the one that you want, and you will be wrong because you shouldn't be caring about such things. By the way, everybody is going to look at the termination handler thing. My advice on violation handlers is don't write one. Use the default one. Keep using the default one until you decide that, oh man, I really can't live with that anymore. Then write your own. And in fact, even better, before using the default one, use quick enforce. If quick enforce works for you, it will be better than anything it'll be better than regular enforce, and it'll be better than anything you could write, if it works for you. So start with quick enforce. If you can't use quick enforce, use regular enforce. At that point, you're probably doing it because you have to write a termination handler or a violation handler. And then, yeah, if you really have to, write the violation handler. But don't go there right away. Any other questions? Okay, I guess that's it. Thank you.